capacities of wind, solar, and storage required to achieve hourly matching of demand with carbon or clean electricity are reduced when we increase the share of computing jobs, and that means the share of power loads that are flexible. So, in short, demand flexibility makes carbon-free computing more resource efficient.
Hello, and welcome to Environment Variables, brought to you by the Green Software Foundation. In each episode, we discuss the latest news and events surrounding green software. On our show, you can expect candid conversations with top experts in their field who have a passion for how to reduce the greenhouse gas emissions of software. I'm your host, Chris Adams. Hello, and welcome to another episode of This Week in Green Software, where we bring you the latest news and updates from the world of sustainable software development. I'm your host, Chris Adams. When we talk about green software, we often talk about code efficiency because it's something that we're often already familiar with. But as you learn more about integrating sustainability into software engineering, you end up learning more about the underlying power systems that all our servers and end-user devices like laptops and phones rely on too. And because the power systems we rely on are in the middle of a generational shift from fossil fuels to cleaner forms of energy, there are changes taking place there that can inform how we design systems higher up the stack. This summer, a team of researchers from Technical University Berlin published a study in collaboration with Google to help shed light on this emerging field. They modeled the entire European energy grid with open source grid modeling software written in Python, along with a set of internet-scale data centers to better understand how scaling their use of compute to match the availability of clean energy can affect the associated environmental impact with running this kind of infrastructure. This was interesting enough, but the modeling also revealed some interesting findings about the cost of transitioning to digital services that run on fossil-free power every hour of every day. This sounded like absolute catnip for sustainable software engineers. But because this is also one of the first open studies published around carbon-aware software, it's possible to understand the assumptions behind these results and figure out how they might change in future. So if you want to learn a bit more about this, to help in this quest, joining me today, we have one researcher from the Department of Digital Transformation in Energy Systems at the Technical University of Berlin, Iegor Riepin. Hey, Igor.
Hi, Chris. Thanks for having me today.
Igor, it's lovely to hear from you again. Before we dive into the world of grids and carbon-aware software and the like, can I give you just a few moments to introduce yourself?
Yes, of course. Hi, everyone. I'm Iegor Riepin. I'm postdoc researcher at the Technical University of Berlin, where I'm part of the Energy Systems department. In our department, we use methods from operations research and mathematical optimization, researching the cost-effective opportunities for climate neutrality. This means I spend most of my time writing, solving, and debugging mathematical models of energy systems. Our research group also maintains an open-source Python environment for state-of-the-art energy system modeling, which is available at pipesa.org and github/pipesa.
Okay, cool. Thank you for that. So I know that I actually met some of the folks in the same department as you from actually an event called Clean Coffee that I used to run at climateaction.tech. Tom Brown came along to one of those Zoom calls back in 2019, and from there we just kicked it off. And that's how I found out about anything going on in Berlin. And I understand that you've been in Berlin for a while, but you weren't always studying and working in Berlin. You've been in other parts of the world as well, correct?
Yes, that's right. I'm originally Ukrainian, where I lived up until I was 20 or so, and then I moved to Germany to make my master's studies, then academic career. Before Berlin, I was doing my PhD in the Brandenburg Technical University, where I worked with Professor Felix Musgens, and I worked on my PhD in various questions of modeling energy systems. When finishing PhD, I joined as a postdoc Tom Brown's group in TU Berlin.
Cool. All right, then. And that's how we ended up here, then. Okay, so we're just about to dive into the meat of the show. And here's a reminder that everything we talk about will be linked in the show notes below in this episode. So if there's a project mentioned or a site or a paper that we refer to, please do write in and tell us so we can update the show notes for other curious souls and help you in your quest for knowledge. All right, Igor, are you sitting comfortably?
Yes, I'm standing comfortably.
Okay, all right then, let's begin. So it's really tempting to jump right into the nerdy specifics about this research and so on. But before we do, can you share a little bit about the background from your current research for this to provide the context for the work that we're about to discuss?
Yes, of course. So over the past year and a half, my colleague Tom Brown, who is the head and the heart of our research group, and I have been working on the open source model-based research dedicated to various aspects of 24/7 carbon-free electricity matching. This concept usually goes under the name hourly CFE matching. The 24/7 CFE is a new approach for voluntary clean energy procurement, where companies aim to match their electricity consumption with carbon-free or clean energy supply on an hourly basis and around the clock.
Okay, so let me just check if I understand there. So normally when people say they run on green energy, they might be talking about things on an annual basis. And this is so hourly. So it's 8,760 hours in a year. So it's 8,760 times higher resolution. So you don't have this whole thing where if you say you're running on green power, you're not making a claim of running on clean energy at night, for example, something like that, right?
Yes, exactly. That's pretty much about that. So it's interesting because the 24/7 carbon-free energy hourly matching aims to eliminate all greenhouse gas emissions associated with electricity use of an energy buyer. So the strategy also aims at addressing the main problems that exist in matching demand with clean energy supply when using so-called established certification schemes. The audience of the environmental variables might know all of this pretty well, but I'll just name a few to outline the context. So companies who would like to demonstrate their sustainability credentials might opt for buying the guarantees of origin. This has a story related to Europe, or the renewable energy certificates or renewable energy credits. This is a story related to United States. A common feature of these schemes is that renewable energy credits are, so to say, unbundled from megawatt hours of energy. When using the schemes, there could be several problems that would arise. So one of the problems is that assets procured with these credits, or the credits you procured from certain assets, this might not be additional to the system. This means if you buy renewable credits or guarantees of origin from an asset located in Norway, and the asset was located in Norway, is located in Norway, and will be located in Norway, no matter what your procurement, it's hard to claim the change of the system associated with your matching strategy. The second problem is typically arising with using guarantees of origin is so-called mismatch in location. So if demand is located in Germany and the energy asset generating the renewable credit is located in Spain, there will be hours when the grid between Spain and Germany is congested. So it creates a counting problem, and likely no those electrons were consumed that were produced. So these two are the so-called additionality problem and locational matching problems that arise with guarantees of origin.
Okay, so if I just check if I understand that. So one of these issues was about additionality you mentioned. So if I understand what you're saying is, let's say that you got some form of generation. Yes, you get paid for the power you generate, but there's another thing that people are paid for, which is like the kind of greenness. And this, as you say, ends up being unbundled and traded separately. And you basically a bunch of problems tend to happen once they're unbundled in that scenario there. So you spoke about something in Spain, like, yes, there might be a grid where you could theoretically have a solar farm in Spain generating electricity, but whether it's actually really deliverable to somewhere in Germany is another matter, because it might not be physically possible to deliver that power. So this is some of the kind of complexity that it's trying to address here, if I understand that, right?
That's correct. And some energy buyers do think about this and recognize these problems, and they opt for power purchase agreements. These are bilateral contracts between buyer and supplier. And when signing power purchase agreement, these companies would pledge to buy both the energy, so megawatt hours, and the environmental credits bundled to it. The problem here is that under power purchase agreements, renewable energy supply is typically matched over a long period of time with buyer's energy demand. So, for example, there is plenty of companies who are joining the known Renewable 100 group who claim to procure right enough renewable electricity to match their consumption on an annual basis. The problem here is, guess what? Renewables are not generating at all hours throughout the day. And this concept is sometimes called in the literature as renewables are non-dispatchable. Sometimes it's called that they're intermittent. Sometimes people say that renewable energy is variable. There was a recent awesome podcast from Volts where the host, David Roberts, had Jason Jenkins, who suggested the term weather-dependent fuel-saving technologies, which I think is an excellent way to put it forward. And this is a way we will likely use it today. So when energy buyers sign PPAs with weather-dependent fuel-saving technologies, there definitely will be times when generation is low, so energy buyers have to depend on procurement from the local markets that likely have some carbon content in it in a given point of time.
Okay, so just a quick translation. You said weather-dependent fuel-saving technology. That's opposed to, essentially, if I'm going to be burning gas or coal, I don't have to care so much about the weather, but I'm having to burn a bunch of stuff. And the whole combustion of fossil fuels is one of the problems we have here. So that's how you might frame it, right? So, because once you've built something, you don't, presumably once you've got, say, wind or solar or something like that, it's renewable. So you're not having to purchase the fuel. That's the distinction that we have there, right?
So the term which I referred, which was coined by Jesse Jenkins in that podcast, referred to weather-dependent fuel-saving technologies, refers to the concept that when we use renewables, we do not have to buy fuel, which comes at cost. We do not burn fuel, which comes with carbon emissions associated with burning it, and we don't have to think about the fuel.
Okay, all right, thank you. Now we've got some of these terms sorted out now. Now we can talk about how some of this might work in the context of data centers and things like that. So maybe I should ask you a little bit about this study. So we've done this work now. Now maybe you could just talk a little bit about what the study that you were doing with Google and with TU Berlin was about for this.
All right, so we have an ongoing research project where we collaborate with Google. As audience might know, the company has claimed a commitment to achieve 24/7 carbon-free electricity matching in all of their data centers worldwide by 2030. And from our side, we bring an academic look to a broad range of questions relevant for making data centers and more broadly, any consumers from commerce and industry sectors carbon-free. These questions are like, how can one achieve hourly matching of demand with carbon-free electricity? At what cost this comes? How can advanced tech help? Or what would be the impact on the background grids? We released a series of open studies aiming to address some selected aspects of this complex question. So where demand flexibility comes to the story? So demand flexibility is the degree of freedom that companies pursuing their goal of reducing carbon emissions can use and benefit from. This refers to a broad range of companies with various degrees of flexibility, which takes many forms and colors, mostly of temporal demand management. And perhaps even more interesting, this refers to demand flexibility of computing infrastructure or data centers that can be geographically scattered and managed collectively by one entity or one company. So data centers as electricity consumers have some special perk. They have an ability to shift computing jobs and associated power loads in space and time. And in July this year, we released a new study where we focused specifically on space-time load shifting problem. So we look at the role the space-time load shifting can play in reducing the costs and resources needed to achieve perfect 24/7 matching. We thought about the signals that companies can use for shaping their load. And we also looked at the trade-offs and synergies that derive from co-optimization of spatial and temporal load shifting.
Okay, so I'll just try to make sure I follow that from a kind of layperson point of view. So there's basically maybe two things that came out of that. So one of these things is this idea that in addition to, if we know that the amount of power we might be generated from clean sources might change over time, it sounds like there is a chance to, rather than have to generate more, just actually make supply and demand match just by scaling back some of your own energy usage. And this is something that isn't just done inside the technology sector. For example, I know that buildings might do this to cool a building down when the energy is cheap, for example, at night, so that when you walk in, it's nice and cool, for example. Or if you're in Texas or somewhere, boy, it's a nice, comfortable environment. So that's the kind of moving things through time. And that's one temporal thing. But there's something special about computers and data centers in that rather than just moving the energy, you can move the work to somewhere else where they have an abundance of power. And that's the kind of special thing that you ended up doing a bit of studies into, right?
Yes, exactly. We focused both on space and time flexibility. We write in the study that space-time nowadays mostly is a story of computing infrastructure, data centers. The temporal flexibility applies to a broad range of companies who have various forms of temporal demand management.
Okay, cool. All right then. So we've spoken about that, and as I understand it, maybe I should just ask a little bit about, so what's the benefit of doing it this way? Like, why would you even think about trying to match some of this stuff up rather than just like buying a bunch more green energy, for example, or a bunch of new solar farms?
Well, thinking about this, imagine a company with an inflexible demand wants to match its own consumption with carbon-free electricity. It could source carbon-free electricity from various sources. This could be a combination of grid imports, if the grid is clean or clean enough for your purpose. It could be generation of renewable generators procured with power purchase agreements, and dispatch of storage assets if storage assets. This is a pretty challenging task, since battery storage is helpful for bridging some hours of no wind, no solar, but it's not the right technology, or better frame, not the right economic technology for times when you need to firm weather-dependent wind and solar over an extended period of time. So pre-research done by Princeton University, Net Zero Lab, folks from Peninsula Clean Energy, and also from us last year, did show that 24/7 CFE, hourly matching is possible with commercially available technologies like wind, solar, and lithium-ion batteries, but it comes at large price or cost premium and with some curtailment of renewable electricity. If consumers following hourly matching have an access to advanced tech like hydrogen storage or clean firm technologies, their price premium could be reduced. Data centers could use this special perk, so the ability to shift loads over space and also time, to relax this problem of matching demand with carbon-free electricity supply.
Okay, so what I think you might be referring to here is the fact that because there's this flexibility, that reduces the amount that you need to buy to have ready to match the entire time. So it may be that you don't need to buy so many batteries or have so many wind turbines or something like that, yeah?
Yeah, so put it simply, you can move loads from the places where you have access to the loads where you don't have enough carbon-free electricity, and by moving these loads, you could possibly save potential storage needs, and you can also save or reduce the amount of excess electricity you would have that you might have curtailed otherwise.
Okay, and when we just briefly touch on curtailing, that means that rather than just wasting, not being able to use this energy, you're able to put it to use to some kind of productive use, which basically improve the economics, means like you might reduce the cost of running something, for example. So it might pay for itself doing something like this.
Exactly. If you have signed PPAs with an asset or you built asset on site, you likely have some excess of energy in some hours. You could sell this excess to the background grid if the background grid takes it at a price. You could potentially store it, but you would store it up until point the storage is economical, and some part which you would not store or you would not sell, you would typically curtail.
Okay, cool. And curtailing, and for the purposes here, is basically having to throw it away because you can't use it productively. All right then. Okay, thank you for explaining that. So we spoke a little bit about some of the details on this, and it might be worth just briefly touching on some of the open approaches for this, because you've mentioned a tool called PIPESA, which I think is Python Power Systems Analysis. It's something like that, right? And the open part of the study is quite a key thing for this project. Is that correct?
Yes. So we use PIPESA, which is open source Python environment for state-of-the-art energy system modeling. This is a tool which our group develops for and maintains for our own research, but also it's been used by a wide range of companies, institutions, NGOs, TSOs, by some others who might find a use in open source tools. So PIPESA itself stands for Python for Power System Analysis, as it was originally scoped for the power system analysis. However, nowadays the tool is used for many other applications but for power, which includes transport and heating and biomass, industry and industry feedstocks, some carbon management, sequestration, hydrogen networks, and what else. So the open source Python environment in which we ship or which we maintain includes PIPES itself, which is a modeling framework, but it also has several individual packages that make it possible to go all of the way through the data processing, such as calculating renewable energy potentials in different countries that we model, or collecting energy assets data, to creating and solving complex energy optimization problems. So why would open source modeling be interesting? There are a couple of things which usually comes in place answering the question. This could be transparency and credibility. So by doing open source modeling, we show that we have no cherry-picked assumptions in our studies that would drive certain results. Open source is also pretty useful for reducing wasteful multiplication of work. We can think about it, so there is plenty of energy modeling groups in academia worldwide, but also energy modelers in consultancies or in industry. All of us are doing basically the same job. But if all of us have to create an airplane
model,
before we fly the airplane, we are not progressing much. And doing open source is quite helpful to, sometimes you can just copy from somebody who did a good job and put it in this open license and go ahead.
Okay, cool. That's actually, so that sounds quite exciting. So essentially, if someone's going to say, oh, I think we can decarbonize this industry by this date, you can essentially model it and say, these are the assumptions I'm making. This is why I think it's possible. This is why I think we can afford it. And this is how much I think it would cost, for example. And the idea that because it's open, it becomes easier for, say, policymakers or civil society to basically say, hey, you've made a really weird assumption here. I challenge that, and vice versa. And with it being open, although we've mentioned Google a few times, this could be used by any company or any organization that might also want to see if this would be applicable to them for running any kind of infrastructure themselves. Is that about right?
Yes, when we do, for example, our study, which we today talk about, which is released in GitHub on a special Git release, and everybody who can run a Python script could reproduce our results, could see how our assumptions are formed, what we put into our optimization problem as parameterization, and if you wish, you could basically get the same result on your local machine. Okay. If you have this way, you can be pretty sure that we did not do some cherry-pick stuff to shape or drive results in one and this direction.
Okay, cool. That's really interesting. I didn't know that I could model the entire European grid on my laptop to actually try and settle a bet in the pub. That's quite cool. All right, then. So maybe let's go back to this study then. So we've spoken a bit about this, and we haven't actually really discovered or discussed the findings. So maybe I could actually ask you, are there any particular key findings you'd like to share so far? Or is there any nuance we should be aware of before we dive into some of the kind of juicy results here, for example?
Yes, sure. I think we could address this nuances topic first. We could just briefly go through the study design and key assumptions driving our results so the audience would understand where from. So for this study, we used the computer model of the entire European electricity system. With this model, we simulated the hourly operation of the electricity system and the so-called system development. So we looked at the cost-optimal investments system would have in generation and storage assets for the modeled here. We placed 5 data centers in, and we chose the regions where we placed our data centers so as to capture grids with different sets of features, unique renewable resources, and national characteristics. We assume the data centers have a nominal load of 100 megawatt for simplicity. This assumption of what is exact nominal load of data centers doesn't play any big role in the results. If we have smaller or higher capacity assumption, we would observe same trends.
Okay.
And we configure our mathematical problem that all data centers follow 24/7 CFE goal. So to achieve this goal, data centers can co-optimize electricity procurement from the local grid and procurement of additional resources such as storage, wind, PV generators that are additional to the system and located in the same median zone. And we assume that data centers have some degree of load flexibility, which we vary with scenarios. Stepping from 0%, which would mean that there is no flexible workloads, so all loads are inflexible and must be served at places of data center location, up to 40%, meaning that 40% of data center loads are flexible and can be shifted to other places or delayed to other times. This is what we do. What we do not, first, we do not quantify the actual costs and technical potentials of achieving certain share of flexible workloads. We just say, hey, this data center fleet have some share of flexible workload. How would you optimize the flexibility utilization and what benefits it might bring? We also treat data centers simply as large consumers that can shift a certain share of loads, which is not too far from reality. But what I mean here is that we abstract from the technical aspects and properties of flexible workloads and some physical constraints of quick ramping. There is tech folks who could focus on these topics with their knowledge. And we base our model inputs only on freely available raw input data. So for electricity systems, we parameterize the system mostly from Danish Energy Outlook. And for data centers, we assume pretty generic, transparent assumptions. By this, we try to keep our study design broadly applicable for other companies who might have their specific flexibility shares or forms or shapes. And we try to keep our workflow available at GitHub for everybody to access and reproduce.
Okay, so if I understand that correctly, essentially you're doing this with as much open stuff as possible so that someone can reproduce this. And the assumptions you're making about these data centers, it doesn't, although the size doesn't matter that much, 100 megawatts is that's like a medium-sized to large hyperscale data center. So this is, again, it's somewhat reflective of the reality. And you also mentioned that they're in different parts of Europe. So from memory, I think this was like Ireland, which is like windy and in the west, Denmark, which has loads of wind. There was like a few other places in Europe as well with different kind of generation and different geographics. So they're in different places. So it was somewhat representative of the regions we might use in cloud, right?
Yes, so data centers eventually were scattered in Ireland, Denmark, West DK1 zone, Finland, Germany, and Portugal. The idea was that we would take regions with different renewable resources. First, the regions that would be pretty far from each other, and also we would take regions where there is data center consumption in national energy mix. And by that, we take different enough regions and we would capture all the system dynamics that we would want to.
Okay, cool. That sounds somewhat, I can recognize that with my kind of cloud hat on, thinking about running something in Ireland versus running it in Germany in this scenario. Okay, well, that sounds like we've given enough background for this. Should we dive into some of the findings? Is there anything you'd like to? So yeah, maybe I should ask, what was maybe one of the first findings that really caught your attention that you'd like to share from this?
So I think we could go through several steps. The first findings that usually has been caught by people looking at our study is this topic of resource efficiency and cost reduction. Just for audience to understand, from our model, as a result of optimization, we get procurement strategies for each data center, which optimize to match demand with carbon-free electricity around the clock with some desired quality score. So the cost-optimal technology mix that we get as an output depends on various factors. For example, renewable resource, this would be wind to solar average energy yield, or our cost assumptions, and many more. So the clear trend that we observe across all scenarios is that capacities of wind, solar, and storage required to achieve hourly matching of demand with carbon or clean electricity are reduced when we increase the share of computing jobs, and that means the share of power loads that are flexible. So in short, demand flexibility makes carbon-free computing more resource efficient. What we also could do, we could retrieve the cost of any procurement strategy from our model, and thus we can map the resource efficiency to the cost effectiveness. meaning you pay less to achieve exactly the same. So the degree of this cost effectiveness scales with the level of flexibility that we assume. So for the corner scenario, where we assume the 40% of flexible workloads, perfect hourly CFE matching, and co-optimized space load shifting, the overall energy costs of the model data center fleet are reduced by up to 34%. So this refers to the cost saving of an individual data center, but it refers to the cost saving of a group data centers scattered geographically and managed together by one company. So these data centers consume basically the same amount of megawatt hours, but do shift their consumption in space and in time to optimize the resources.
Okay. So if I just trying to run that by you so I understand. So essentially, you model different amounts of flexibility in a system if you're controlling multiple data centers here. And essentially, the more flexible you make it, the more you can actually reduce the amount, the cost of actually having to buy all these solar farms and wind turbines and batteries, and all the way up to the point where if you've got 40% of your loads being flexible, then it reduces the costs by about a third, essentially. That's what I think you're saying there.
Yes, that's right. But we should see it in perspective that this 30% cost saving is basically our corner scenarios. We scale the cost very up. So scaling very up means we look at the perfect matching between demand and carbon-free electricity. 100% that you are not allowed to have any gram of CO2 per kilowatt hour of consumption. And also we assume in this scenario that 24/7 buyers only have access to wind, solar, and lithium-ion storage. So this is a palette of commercially available technologies which are just hard to use out of these technologies to make 24/7 strategy. If these two are right, then your costs are reduced by up to a third, and the costs are reduced less than that for all palette of other technologies and scenarios that we consider in the study.
Okay, cool. Well, thank you. That was bigger than I was expecting it to be. That's pretty impressive if you're going to be spending literally billions on power, like some large data center providers or data center users will be using. Okay, then, Igor. So, if I understand correctly, the amount of flexibility you might introduce, this kind of carbon-aware computing, that if you say that you need to be running everything on 100% carbon-free or fossil-free or clean energy based on this, then this will reduce the amount that you need to purchase, which essentially makes it more affordable or more accessible to a wider number of operators, I suppose. Are there any other findings that you would draw attention to in this study?
Yes, of course. What we do in the study, we take a look on the signals that companies might use to shape their load-following strategies. So to discuss these signals, we could firstly go for spatial shifting story and then for temporal shifting story. So for the spatial shifting story, the one signal which comes up front is the fact that outlet profiles of wind power generation have a low correlation over long distances due to different weather conditions. So as a rule of thumb, you can think of the following. If two generators are located as far as 200 kilometers from each other, the hourly feed-in from these assets have very low correlation, and data centers could arbitrage on this effect, or put simply, they could move load to locations when and where there is a high wind generation, thus saving the cost of energy storage and thus reducing the amount of solar curtailment. So the hourly profiles of wind generation is not the only signal. Another signal that we discuss in the study is the difference in quality of renewable resources in regions where data centers are located. So the quality of wind of local resources, or in other words, the average capacity factors of wind or solar PV in a given region, they translate to the cost of electricity. The higher the quality of renewable resource, basically the lower the average cost per megawatt hour. Special load shifting is possible. A rational buyer could just adjust own procurement strategy to contract generators in better locations. So those locations where renewable assets have lower costs, and co-optimize special shifts accordingly. In a study, we illustrate this mechanism with a data center located in Ireland. So it's not the most sunny region in Europe, that would tend to shift loads away during daytime through mid-spring to mid-autumn. So data centers located in Germany and Portugal, the regions with much better solar resources than in Ireland, they would tend to receive loads during this period. This picture would just work about reciprocally for wind-related load shifts. Data center in Germany would benefit from having partners in Denmark or Ireland that have much better quality of wind resources. And so there are two signals for spatial shifting. There is one more, which we did not put much of focus in our study because of our geographical focal scope, but it could play a role for spatial load shifting. So if you look above Earth from the North Pole, and the Earth would rotate counterclockwise from west to east, and we are pretty sure that it rotates with a constant predictable speed, roughly once per 24 hours. So if data centers are scattered across the globe in distant locations and operated by one company, one could imagine a load shaping strategy where loads would follow the sun.
Yeah.
So these are basically three signals for spatial load shifting. For temporal load shifting story, we illustrate cases when the variability of the regional grid emission intensity could drive the carbon-aware temporal load shifting. So the grid signal can play a role in load shaping strategy if data centers have electricity imports from the local grid in their energy mix. And the temporal flexibility could also be helpful in aligning the demand in time with the generation of procured renewable resources.
Okay, so it sounds like there's almost two kind of scales that you're working at here. So the first thing you spoke about with, like, say, Ireland and Germany and Portugal was like, essentially, so basically Germany and Portugal are sunnier and Ireland is windier. And during the summer, they're going to be, Germany and Portugal are way sunnier. So if you were running, say, computing in these three places, you might choose to run more of it in those two during the summer. And then as it gets a little bit darker, you basically choose to run everything in Ireland instead. And that's going to be a much more efficient way to essentially run, maybe if you're going to run computing jobs at 100% carbon-free energy, that's a way that you can do that at the lowest costs. So there's one thing happening at an annual level, but you also said there's a kind of another thing which is much more tied to the kind of day and night cycle that you're referring to as well there. So there's different speeds that you might be thinking about and different trends that you might take into account.
Yes, we talk about pretty complex optimization problems that spans across space, spans across time, and the signals that would drive optimal utilization of flexibility through this space-time graph have various shapes. Some signals have stochastic pattern, like wind and feed, which is uncorrelated over long distances. Some signals have predictable pattern, like solar profiles that follows the Earth's rotation, and some signals have something in between predictable and unpredictable.
Oh, cool! Wow, I wasn't expecting that. Yeah. So we spoke before about, okay, one thing that you could do is essentially during summer, you're running your computing jobs in Germany and Portugal where there's loads of sun and loads of clean energy, and that's quite relatively cheap. And then in winter, you'll choose to run it maybe Ireland or somewhere where it's a bit darker, a bit gloomier, but way windier, and where there's oodles of green energy there. But you said there's some trade-offs that you have to make here if you were to choose this. Maybe you could just expand on some of that a bit more so that people understand, so that it doesn't sound too good to be true, for example, or so people understand some of the specific nuances here.
Yes, very right. What we do in the study, we take a look on scenarios where we co-optimize and isolate utilization of spatial and temporal load shifting. So these scenarios with isolated flexibility can be seen by just academic exercise, but it's pretty useful for us to take a look on the system mechanics and get a feeling of the numbers. So as a result of optimization, we can retrieve the value which would represent something like reduction of the overall annual energy cost of a carbon-free electricity supply if a data center utilizes either spatial load shifts or temporal load shifts or both. If we compare the value of spatial and temporal load management when spatial and temporal stories are isolated, we come to the numbers of something from 6 to, depending on scenario, in favor of spatial load shifting. So this means spatial shifting workloads across locations brings you 6 to 1 higher value. And this takes place because data centers can arbitrage on differences in weather conditions and take advantage of. So this is the mechanism which we have just discussed. Shifting workloads across time to bring a high value requires a few things. So for that to have a high value, data centers would need to buy electricity from the background grid, which is high variability of the regional grid carbon emission density. So if a local energy mix is flat dirty or flat clean, there is no basically value to shifting workloads from one time to another. And the trade-offs would appear between spatial and temporal load shifting when both are implemented together. So one can think about this in this way. If you have a certain share of flexible loads and you would like to shift some in space and some in time, but whatever you shift from other places and other times cannot exceed the upper cap, which would be the computing capacity constraint, and whatever you shift away, that means to other places or to later times, cannot exceed the lower cap, which would be the flexible workloads cap. And one thing on synergies, what we do show is that co-optimization of space and time load shifting can yield benefits that go beyond the value of each of the two individual mechanisms could bring along. It's sort of an expected outcome for any operations research problem. If you have 2 degrees of freedom and you co-optimize them, you could co-optimize in a way to get a benefit from synergies of them both. So in the study, we come to this point from various angles, but here's just a good example. Imagine if you have, say, 3 data centers scattered far from each other and operated by a single entity. Then imagine we have each data center which has a mix of wind and solar capacity built on site, and assume that this data center can shift workloads with any fixed volume of flexible workloads. Now somebody comes and says that, hey, we have one long-duration energy storage asset that we could place in either of these 3 data center locations.
The big ass battery, basically, yeah?
Yeah. The question is here, where would you place it to reduce the energy costs in the entire system? If we would write optimization problem for this, solve it, we would tend to see that the optimization problem suggests us to harvest renewable electricity in the best locations, so those locations where the lowest cost per megawatt hour is achievable. For example, Denmark, Ireland with good wind conditions. And indirectly opening access to this cheap, clean electricity for all locations through the spatial load shifting.
So that thing you mentioned there was, you got this notion of moving things spatially or moving things temporally through time. So it's essentially, you get more of a gain from moving things geographically, spatially, if you're going to do nothing, if you just only do one. But that can be a little bit harder for organizations. So there is some gain from doing things temporarily, but on the temporal scale, you do need the grid to be a little bit more volatile, moving back and forth between very sunny and then not very sunny, for example. So they start using go back to dirty energy, essentially. But the thing that you can do is these do work together. So you can move through time and space, and you do end up with basically the benefits do compound in this case here.
Yeah, and it's worth saying that the benefits actually do not compound simply together, because the spatial and temporal stories are subject to the shared set of computing capacity constraints. So when you co-optimize both, you inevitably have to trade off among them.
Okay, compound is the wrong word then. All right, but basically, by doing the 2 things together, you can get a better saving than just doing one of them by themselves, for example.
Yes, correct.
Okay, all right then. So we've spoken about this, how it's been applied to one company, and we've said that this could be used for multiple organizations. Presumably, if someone wants to do this, you could do this for an entire sector to figure out what the power might be needed for an entire sector, to see how much you might need to deploy to displace all the kind of fossil-based energy generation that data centers use, for example. Is that plausible that you could do something like this with this kind of modeling?
Well, in our study, we try to keep our assumptions on carbon-aware computing in the way how we treat data centers, how we treat flexible workloads, as general as possible. So the study results should be applicable to the broad range of companies operating data centers with their specific features and their specific workloads. And as well as the study should be applicable to a broad ranges of companies from commerce or service or industry sectors for which, say, only temporal story is relevant. One cool thing here is that data centers can pave the way for space-time load shifting applied for other industries and other applications we are not yet even aware about. So just to mention, I recently visited the group in the University of Wisconsin-Madison. It's the Victor Zavala Scalable Systems Lab. So this is a bunch of awesome people. I spent with them 3 weeks. I'm not really sure what they work about because they work about on computational chemistry, on energy systems, on graph theory, optimization, stochastic programming. I think they crush every problem that people are throwing at them.
Yeah.
And when I was there, they were launching a new project which was focused on exploiting space-time interdependencies between electrochemical manufacturing and power grid. So the idea here is that electrochemical industry would shift loads to optimize the economics and to reduce the carbon emission intensity of the electrochemical manufacturing, which is pretty awesome, because before I thought that space-time shifting is more about data centers only. But now, well, there are applications beyond only this sector, and I think it's the future where we are going to.
Okay, so basically, as more and more clean and variable fuel saving technologies come onto the electricity grid, it's going to get more and more kind of uppy downy variable. And it's not just data centers this will be applicable to. So electrochemical stuff would be like synthesizing fuels or making plastics or things from carbon captured from the air, for example, or things like that. I think Tom Brown mentioned a little bit about making methanol in this kind of way, or some of the green hydrogen stuff around splitting water into hydrogen and oxygen for creating chemicals that way. So is that what you're referring to in this scenario?
Well, I don't know what they will do in the project. It would be very interesting to take a look. I'm not sure that it's very simply mapping one to another. So for data center, special shifting means that you move workloads and associated power loads from one place to another. But this moving means that just computing jobs are being executed in one data center and not in another data center, while the end consumer is somebody waiting for the YouTube video to be rendered, consuming the good at the place it would be consuming no matter the shift. How exactly it works for the electrochemical industry, not sure, but we will see once the project is developed.
I see. Okay, cool. All right. You mentioned one thing about this being something which is more generalizable to a wider set of technologies. And one thing that actually this makes me think of is a new paper that was published by Facebook. They have a serverless platform which they call XFAS. And one of the key things that they were doing is actually having this kind of geographically movable computing that they refer to. And one thing that really strikes me is that Facebook basically said by allowing the actual computation to be flexible in terms of where it's actually run, they were able to massively increase the use of the data centers they were using. So if you think about it, for most data centers, they might be at single-digit percentage utilization. So most of the time, not doing very much. Cloud might be estimates of around 10 times more efficient. So maybe 20 to 30% efficiency for most very well-run hyperscale data centers. Facebook themselves say that by introducing some of these ideas, we've been able to get up to 66% utilization, which basically means there's a bunch of extra hardware that they don't have to buy and build, which is good because they are spending lots of money building data centers in lots of places. And anything that you can use to reduce the number of data centers you need, in my view, is a good thing because that's a lot of buildings that don't get built, for example. But the key things they mention in the paper, and we'll share the link to the paper, is that if you have maybe a computing job or you've got a function or anything like that, you basically have they make this stuff possible by adding kind of deadlines or saying how tolerant of being moved through time or moved through space a particular job might be. And this feels like this kind of hints that this might be a way that might become a norm for working with computing, where if you don't need to have something happen right away in the same place, then you can basically get all these extra benefits by being a bit more flexible about this and saying this stuff up front when you submit a job to a computing cluster or something like that.
And it's pretty relevant to ask question. It's not only what are the benefits for the operator of the data center, but what are also the benefits more broadly to the background system in terms of costs and emissions.
All right. Okay. So I know that you released this study in the summer, and there's some stuff which people can refer to here. But I also am aware that we are in a fast-moving field, and you just mentioned some work in the University of Wisconsin, I think. Are there any other things you would like to have included into this kind of research, or you think people should be looking at over the next 12 to 18 months inside this that might influence how people might think about carbon-aware computing or flexible computing like this with a view to reduce the emissions associated with running infrastructure that we all rely on right now?
Maybe one study or research paper which I would love to see is that if somebody would take the courage and to illustrate the system-level benefits of carbon-aware computing across different contexts and different states of the system. So by system-level benefits, I mean from society perspective, so we'd look at the costs or total carbon emissions or total curtailment of renewable energy and so on. And by different contexts and states of the system, I mean the following. So let's think nowadays, there are mostly companies who buy electricity from the local grid. They have some flexibility. They would go to the data providers, such as electricity maps, providing the short-term forecasts or carbon emission intensity, and they would factor it into their load following strategies. This can work for the temporal shifting, also soon will work I believe broadly for the spatial load shifting. So in this case, space-time shifting can help if you just buy from the grid. So there is a follow-up to this. So some companies might go beyond that and buy additional resources to eliminate all of their carbon footprint completely. So for that, space-time shifting could also help, and this is basically what our study is about. It would help you to be more resource efficient, it would help to be more cost-effective, it would open 24/7 CFE for a broad palette of companies who would not maybe jump there otherwise because of high cost premium. And in the future, we will hopefully be reaching the net zero electricity systems, or more broadly, net zero energy systems. And space-time shifting can be of help there too. So we would need some set of solutions where we would firm the variable wind and solar. We could think about a palette of solutions on the supply side. There could be grid-connected battery storage. There could be hydrogen storage if in a region where there are salt caverns. Or there could be even energy storage in the liquid hydrocarbons, like methanol storage. My colleagues Tom Brown and Johannes Hamp recently published a journal paper on this. But these are all the solutions from the supply side. There could be solutions on the demand side, where the large data centers that can move a large loads across space and time, they could help the system to firm the variable wind and solar and provide the service for the system and get some sort of remuneration for that. By the way, Victor Zavala group has also published a research paper where they make a mathematical modeling sketching out what type of remuneration they can get for providing the service for the system.
Okay, if I could just quickly stop you there for a second, because I want to check I understood it correctly. You're essentially saying that rather than it just being about looking at the cost only to, say, in this case, it was like one tech firm looking at how much it would cost them, you're essentially saying it's possible to model this to say how much this kind of flexibility can save everyone else if you actually had these providers, like a data center, as a kind of active participant inside the grid, because that might reduce the amount of generation that the grid might need or that society might need. So essentially it's like flipping it around, saying, well, actually, is there some kind of value that can, or are there benefits that could be shared just outside of just the corporate, just outside of that company? Can it benefit other people as well?
Yes, exactly. And more than that. So whenever we look at this context, either company buys electricity from the grid and tries to move load across space and time, either to reduce costs or to reduce emissions, depending on what signals company takes. Or if company goes 24/7 and wants to eliminate all of the emissions and have a high impact on the background grid, or even if we reaching net zero systems. In all of these contexts, space-time load shifting might be of help and might bring benefits, both for the companies operating it and also for the background systems. So if there is a study who would take courage to highlight all of this transition phase and illustrate the benefits for systems, it possibly would be a really good read.
Cool. All right. Well, that sounds like something for people who are curious about playing around with this on GitHub or want to mess around with some of this modeling themselves to see. And I know there are a number of organizations and people like in software development houses who are actually trying to extend various tools like Kubernetes to incorporate some of this stuff so that you can actually see, so you can essentially design from the get-go, just like I mentioned with Facebook. So like Facebook's XFAS paper talks about how they encode a degree of tolerance into this, but I believe that Intel is doing something similar to this for their versions of Kubernetes. We'll share links to that for people who are listening. This has been possibly one of the nerdiest episodes we've ever done, but I've enjoyed myself for this, Igor. Thank you. Igor, before we wrap up, are there any things that if someone has followed this and was able to keep up and was really curious, would like to learn more, where would you direct people to look if they wanted to dive into this some more themselves?
Well, if people would like to know more about our research on space-time shifting or more generally on 24/7, they could possibly visit our GitHub page. So it's github.com/pipesa/24/7CFE. There in README, we explain what is the research we're doing, how to clone our work, on how even to reproduce it. If people are interested in PIPESA ecosystem for open source energy modeling, they could visit pipesa.org, or more generally, if people are interested in the open energy research in general, it is living in openmodinitiative.org, which collects various research groups and open models all about energy. And finally, if there is somebody interested in voluntary energy procurement, one could visit the 24/7 Compact, which is in whole carbon free at 24/7.com.
Okay.
Which is a place collecting people and companies working on this.
Great. And Igor, if people want to find you or follow some of your work directly, is it TU Berlin the best place, or is there an Iegor Riepin on LinkedIn or something that you would direct people to for future questions?
I have my LinkedIn, which I could attach, and there is TU Berlin email.
Brilliant. Okay, well, Igor, I've really enjoyed this. Thank you so much for diving down into the depths of carbon-aware and time-space shifting computing like we did today. Oh yeah, and happy birthday, by the way. I forgot. Yeah.
Thank you, Chris. Thanks for having me today.
All right, take care of yourself and have a lovely week. Cheers, Igor. Hey everyone, thanks for listening. Just a reminder to follow Environment Variables on Apple Podcasts, Spotify, Google Podcasts, or wherever you get your podcasts. And please do leave a rating and review if you like what we're doing. It helps other people discover the show. And of course, we'd love to have more listeners. To find out more about the Green Software Foundation, please visit greensoftware.foundation. That's greensoftware.foundation in any browser. Thanks again, and see you in the next episode.